Welcome back, everybody. This is going to be part 2 of our introduction to moles. And so this video is going to cover a couple of different things. So in the second part of this video, we're going to be distinguishing between the atomic mass of an element and its molar mass. So you're going to find, oh, they're the same, but there's a little different too. Then we also need to describe how the mass of a mole of a compound is calculated. So this is going to be kind of the most important idea for this part of the video. I'm also hoping to include some more conversion factors for these moles to representative particles and representative particles back to moles at the end of the video. On this slide, we're going to be talking about the mass of a mole of an element. So a couple of factoids is to remember that the atomic mass is the average mass of all the elements' isotopes multiplied by their relative abundance. And I'm hoping that you remember an isotope is, isotopes are the same element, they just have different number of neutrons in them. And then we take that number, or its mass number, and multiply it by the relative abundance, and that was just a percentage. We also need to say that the atomic mass of an element is expressed in grams, is the mass of 1 mole of the element. And I know that sounds really confusing, but the cool thing is, for example, if we look at oxygen on the periodic table, we see that its mass is 15.99 AMUs. So that right here, this is the mass of 1 atom of oxygen. Or I should say the average atomic mass of the mass of 1 oxygen atom. On the other hand, if we take that same value, 15.99, and we add a G, meaning grams, now this value is the mass of 1 mole of the element. So let's look at this again. The atomic mass of an element is expressed in grams, is the mass of 1 mole of the element. So notice these values are the same. If we add the grams, then that's the mass of 1 mole of the element. So this is actually a pretty cool concept here. So the molar mass is equal to the mass of 1 mole of the element. I would put another little star here if I could. So remember, the molar mass is the mass of 1 mole of the element. So now when we are going to be calculating this molar mass, one of the things that I am hoping you're noticing is that it says 12 grams is the molar mass of carbon, and so the mass of 1 mole of carbon is 12 grams. But if you were to look on the periodic table, you're going to see it says something like 12.01. Well, in order to kind of help our calculations along, we want to round it to the nearest whole number. So you should notice that again with oxygen. Just on the last slide, we said oxygen's atomic mass was 15.99. Well, yeah, we round 15.99 to 16, and so it's to the nearest whole number. So this is the mass, the molar mass of oxygen, which is the mass of 1 mole. So I'm hoping if these are equal to 1 mole, okay, the mass of 1 mole, how many things are in 1 mole? 6.02 times 10 to the 23rd atoms, okay, or things are in a mole. 6.02 times 10 to the 23rd. So even though these have different masses, they still are going to have the same number of pieces in them. So, for example, if I was to take a mole of chocolate bars or a mole of Skittles, well, the chocolate bars are, of course, going to weigh more because each individual chocolate bar is larger than each individual Skittle, but they would still have the same value of 6.02 times 10 to the 23rd atoms in there. So here's just a quick little check you can do. Just look on your periodic table and just see what the molar mass for each of these is. Just off the top of my head, I'm not sure what zinc is, but nitrogen should be about 14, and I think aluminum is 26, but we might want to double check that one and school me tomorrow in class if I'm incorrect on that one. Since we now know how to find the molar mass of 1 mole of an element, now the next question is, what about compounds? And I know this is cut off, so that's why I'm reading it to you. So it says, in 1 mole of water molecules, there are 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So you want to kind of think of the compound as a molar ratio, and we'll talk about what a molar ratio is later. So it says to find the mass of 1 mole of a compound, You have to determine the number of moles of the element present, multiply the number times their mass from the periodic table, and add them up. So if we were to do water, for example, we would take H, we would take O because those are the two elements that we have. We know that we have two hydrogens in our water molecule and one oxygen in our water molecule, or you might say it's 2 moles and 1 mole, and we would multiply that then by the mass. So the mass of hydrogen is 1, the mass of oxygen is 16, so 2 times 1 is 2, 1 times 16 is 16. Sorry, it's squishing off to the side, so if you were to add this up, our molar mass is going to be 18, so our molar mass for water is going to be 18 grams. Here's a little tougher example. It says calculate the formula mass of magnesium carbonate, which is MgCO3. And so we can see that we're taking, since there's one magnesium, we're taking the mass of magnesium, we're taking our mass of carbon. And now for this one, notice it's 3 times 16, and that's because there's the 3 oxygens. And then our molar mass for this one is going to be 84.3 grams. And notice that they kind of use this decimal place over here. We don't have to do that. We could just round to the nearest whole number. So for us, we would say it's 84 grams is the formula mass for magnesium carbonate. And notice we're using this word formula mass here instead of molar mass. And that's just because magnesium carbonate's an ionic compound, and we use those things called formula units for them instead of molecules. On this slide, I just want to briefly review how we would calculate the molar mass of substances that are compounds. So in this first case, we're going to take carbon dioxide. I would take carbon. I would then take oxygen here, and I have 1 carbon, so I'm going to put a 1. I have 2 oxygens. So I usually put my number of atoms first. Then I'm going to multiply it by the mass of a carbon, and so that's going to be a value of 12. Each oxygen is going to be 16. Do a little math here, 12, 32, and this works out to be, so carbon dioxide has a molar mass of 44 grams. So this basically means that 1 mole of carbon dioxide has a mass of 44 grams, and so we could use this as a conversion factor. Another example you might encounter is something here like chlorine. So even though chlorine might on the periodic table say it's just 35, notice that there are 2 chlorines, so I need to go 2 times 35, so the molar mass of Cl2 is going to be 70 grams. So don't forget, don't let these diatomics freak you out. So I think we're probably at about 7 or 8 minutes right now, so if you feel totally comfortable with information, then bye, and I will see you at the next video. But if you feel like you need some more help with those moles to representative particles, or some more help determining the molar mass of a substance, then continue to watch this video, and hopefully you're writing down these notes. So here's just a couple of example problems. I might not get through all of them, but at least you have the answers here. So what I'm going to do is I'm going to click to the next slide. I'm going to go ahead and solve this one. So it says how many molecules of carbon dioxide are in 4.56 moles of it. So I'll see you on the next slide. So one of the things that I like to do is when I'm about to solve one of these problems is I'll put the given first, and you always want to start with your given. So we were told that there was 4.56 moles of carbon dioxide, and then it asked to get it into molecules. So notice that I put the units down here on the end, just to kind of keep me on track. And then we should have that conversion factor of 6.02 times 10 to the 23rd representative particles over 1 mole to get us into these molecules here. So I'm going to take my 6.02 times 10 to the 23rd, and I'm going to write molecules on the top because that's what I'm trying to get into, and I'm kind of running out of room, and then I'm going to put 1 mole on the bottom. So again, I hope that you guys are seeing why I'm putting the mole on the bottom, because really this number over here, it could be written like this. So this mole is on the top, this mole is on the bottom, should be carbon dioxide, and then we're left in molecules of carbon dioxide, which is what we want. So we would just go ahead and do the math for this. So take 4.6 in your calculator, 4.56 times 6.02 times 10 to the 23rd for your answer. And the answer is on the last slide, so if you want to backtrack on that. And for this one, it should be something like 2.75 times 10 to the 24th molecules of carbon dioxide. Let's go ahead and look at number 2 here. It says how many moles of water are in 5.87 times 10 to the 22nd molecules. So again, here I started with my given, which was the 5.87 times 10 to the 22nd molecules, and I'm trying to get it into moles. So I'm going to use that handy dandy conversion factor again that says that 1 mole is equal to 6.02 times 10 to the 23rd representative particles, and remember representative particles could equal molecules, it could have equaled formula units. There was a lot of things that could have equaled. So where do you think that I should put my mole? I'm hoping you guys are saying that you should put your mole on top. So 1 mole should go on the top because I'm trying to get into moles. Then that makes that my representative particles or my molecules on the bottom, 6.02 times 10 to the 23rd molecules. Now notice my molecules are on top, molecules are on bottom, they cancel out. I'm left with my unit of moles. Bueno, very good. So now I'm just going to take my calculator and divide 5.87 times 10 to the 22nd by 6.02 times 10 to the 23rd. And your final answer for this one should come out to be 0.0975 moles. Now I'm going to go ahead and do a few problems from this slide. And again, notice that the answers are provided here for you. So if you wanted to go ahead and work through all of these, you could, and just come back and double check your answers. So let me go ahead and work through this first one. And it says, how much would 2.34 moles of carbon weigh? So let's go ahead and see, let's figure this out. So I took the very important step of setting up my problem properly. So notice that I'm starting off with my given, and that's how you should set up your problem as well. So I've got 2.34 moles of carbon. And then I'm going to need some conversion factor, which we'll worry about in a second. And we're trying to get into grams of carbon over here. So let's go ahead and figure out how we're going to put our units. Well, since I have moles on the top over here, I'm going to need moles of carbon on the bottom. And I'm trying to get into grams, so grams of carbon will be on the top. And right now you're probably saying, well, that's lovely, Miss Simoneau, that you could put the units in, but I don't know any conversion factor between grams and moles. Well, in fact, you actually do. Remember that the molar mass of an element is equal to 1 mole of that element. So in this case, our molar mass of carbon is going to be equal to 1 mole of carbon. So if you remember back a few slides in this video, the way that we would find the molar mass of carbon is we would look at the periodic table, we would find a value of 12, and that is the value that we would plug in for the molar mass of carbon. And again, that's equal to just 1 mole of carbon. So our moles of carbon, since it's on the top, on the bottom they cancel out, leaving us in grams of carbon. That's what we wanted to do. So just as this is like my math on the fly, I don't know, 2.34 times 12 is going to be like 28. I think there's a decimal in there somewhere, but you can check on the last slide as to what our final answer is. But the more important thing is that you're figuring out how to set up these problems. So let's go ahead and look at the second problem here. It says how many moles of magnesium is 24.31 grams of magnesium. So in this case, we're going to be going from grams to moles. So I'm hoping that you're starting to notice a trend here in the way that I'm setting up these problems. I'm always putting the given here, and then I'm putting what I'm trying to get into here at the end. So I need to go ahead and set up my conversion factor. So I want to cancel out my grams, so my grams will go on the bottom. I'm trying to get into moles, so my moles will go on top. And again, you're probably like, well, I don't know any conversion factor between moles and grams. But remember you do, the fact that the molar mass of magnesium, which is 24, is equal to 1 mole of magnesium. So this value 24 I got from the periodic table. So the molar mass, remember, is equal to 1 mole of the substance. So that's where we're getting this conversion factor. So we just do a little bit of math here. It's pretty darn close to 1. I'm sure there's a decimal there. Just check on the last slide to double check. So I'm hoping that you guys can successfully now figure out the molar mass of a substance, as well as be able to make calculations, simple ones, from grams to moles and moles to grams. Remember to write down any questions that you still have and ask them in class tomorrow.